In part 16 of this series on classical chemical assay for small-scale miners, prospectors, and hobbyists, the discussion was focused on glassware calibration. In this presentation, I'm going to focus on standards and acid-based titrations. I am Rob Boyko, Boyko Mineral Explorations, and welcome back. In titration, as already alluded to, solutions of known purity and concentration are known. Solutions are created and then they're titrated with another known solution and titrated in advance. These solutions of known concentration and purity are referred to as primary standards. Standards, on the other hand, are pure compounds in solution that have known purity, but the concentration is not known. These solutions are titrated to determine their true concentration. Once the solution is titrated with the primary standard and its concentration is known, it becomes a primary standard. Now, this process of determination is commonly referred to as standardization. Primary standard solutions can be created using high purity ACS grade chemicals. As shown in a previous presentation, these are usually 99.95% pure or better. With a calibrated volumetric flask, a primary standard solution can be created to be used as the titrant. Any high purity compound must be completely dry, no hydration. It must also have a known composition. Example, potassium carbonate, which has the formula K2CO3. The compound must also have a large mass weight. The compound of choice for a titration must also be able to react quickly with a standard solution, as well as quantitatively. The standard solution must also be known, as well as being stoichiometric. Any compound used as a primary standard must also be stable in its environment. It should not be hygroscopic, oxidizable in air, or affected by carbon dioxide. In other words, it should remain unaltered during long-term storage and during weighing when open to the atmosphere. The compound must also be totally soluble. Any salts formed during neutralization must also be soluble. As noted, the mass weight or normalized weight must be sufficient enough to reduce a large volume titration. That is, the titration should be less than a burette full. These are just a few examples for acid-based titrations. If a titration was going to be done to standardize a sodium hydroxide solution, a standard benzoic acid could be used. This standard not only has a known composition, it also has a high molecular weight as shown in this table. The pH of the solution at equilibrium, or the neutralization point, is also shown. Now, this pH value can be used to determine the acid-base indicator, which could be used to signify, that is, to indicate the end point of the titration. More on this later in this presentation. Standardization is only a term used to determine the true concentration of a solution through a process of chemical reaction with a primary standard solution. Once the concentration is known, the solution will then be normalized, and the solution's container will be labeled as such. Potassium permanganate, for example, will be the solution to be determined. Sodium oxalate is usually the primary standard of choice. The first reaction equation shows that the potassium permanganate dissociates along with the sodium oxalate. The potassium and the sodium will remain in solution as soluble ions. The remaining ions are the permanganate ions and the oxalate ions. These ions will further dissociate, forming carbon dioxide gas and oxygen, which is liberated as gases. The remaining manganese ion will react with some of the oxygen to form manganese oxide. The first drop of excess potassium permanganate will shift the equilibrium to the right, forming an insoluble manganese oxide compound, which in turn causes the colorless solution to turn purple at the endpoint. Stoichiometrically, the concentration of the potassium permanganate can then be determined. At times, it's difficult to know if a compound is an acid or a base. Commonly used inorganic acids can all be identified as their formulas all have hydrogen atoms listed in front of the formulas, such as hydrochloric acid, HCl, nitric acid, HNO3, hydrobromic acid, HBr, and hydrofluoric acid, which has the formula HF. Organic acids are a little more difficult to distinguish. These, however, will always start with a carbon atom or hydrogen atom as the first atom in their formulas, and end with a hydrogen atom. Examples are acetic acid, C, H3COOH, formic acid, H, COOH, benzoic acid, C6H5COOH, and propanoic acid, CH3CH2COOH. Now, polyprotic acids are made of polyatomic ions and hydrogen. These all start with listing the hydrogen atom at the front of the formulas. Examples are arsenic acid, H2ASO4, carbonic acid, H2CO3, citric acid, H3C6H5O6, and oxalic acid, H2C2O4. Now, bases can be difficult to identify as bases. These will have a polyatomic ion or nitrogen atom listed at the end of their formulas. Some will only be a single polyatomic ion, such as ammonia, which is NH3. Ammonium hydroxide, NH4OH. The hydroxide is a polyatomic ion, which is OH. Sodium carbonate, Na2CO3, as the polyatomic carbonate ion, CO3. And triethylamine has the nitrogen atom listed at the end of its formula. Knowing how to identify a compound as being a base or an acid is important. In the next few slides, equivalence will be discussed, as it is the basis for the normalization of these solutions. Normality was presented in a previous presentation within this series. It's just another way of representing the concentration of a substance in solution. As normality is consistently used in titration analysis of concentration, the focus going forward will be on equivalence and equivalent weight. Equivalent weight is the weight of a substance that either contributes or consumes a set number of ions or electrons during a chemical reaction, whereas the number of equivalents used to determine the equivalent weight is the number of ions or electrons contributed or consumed during a chemical reaction. The number of equivalents is used to calculate the equivalent weights of a substance or substances in solutions. Now, GEW stands for grams of equivalent weight, and the label N has been designated to represent the number of equivalences, although this label is also used to represent the number of moles. It must not be confused with the number of moles. The equation shown that the mass weight of a substance in grams divided by the number of equivalences, N, equates to the equivalent weight of the substance in grams. You see, the table shows this concept. Hydrochloric acid has a mass weight of 36.5 grams per mole. Since there is only one hydrogen atom that can be contributed or consumed using the equation, the equivalent weight for hydrochloric acid is 36.5 grams of equivalent weight, that is, equivalent weight per mole. Same with benzoic acid as having a GEW of 123.0 grams GEW per mole. However, phosphoric acid has 3 hydrogen atoms that can be contributed or consumed. Phosphoric acid has a mass weight of 98 grams per mole. Now, using the GEW equation, the grams equivalent for phosphoric acid is 32.67 grams equivalent per mole. Sulfuric acid has 2 hydrogen atoms, and therefore the number of equivalences is 2. The same equation is used for basic compounds. However, the number of equivalences is based on the number of hydroxide, hydrogen, or nitrogen ions that are contributed or consumed. The polyatomic hydroxide ion, listed at the end of the sodium hydroxide formula, identifies this compound as being basic. It, therefore, has 1 equivalence. The equivalent weight is therefore calculated as 63.0 grams equivalent weight per mole. Magnesium hydroxide has 2 hydroxide ions, or 2 equivalents. The formula for ethylamine shows 2 hydrogen atoms, or ions. This shows that there are 2 equivalences for this molecule. Its equivalent weight is thus 22.5 grams equivalent weight per mole. The trimethylamine has 1 nitrogen atom or ion in its formula. Therefore, the equivalence for this molecule is 1, and the equivalent weight is 29.5 grams equivalent weight per mole. Redox reactions are reactions that will reduce a metallic species to a more pure species. Redox reactions are commonly used in electrogravimetric analysis, as well as electroseparation of species. More on this subject in a later presentation. I also suggest that you locate a free copy of the table of electrode potentials for future use. Now, this equation shows that 1 electron is consumed in a reaction, reducing the iron 3 to iron 2. Since 1 electron was transferred, the number of equivalences is 1. The atomic mass of the iron atom in the periodic table is listed as 55.8 grams per mole. Now, Fe2O3 is the formula for a common rock known as hematite. Dissolving this rock in a solution of potassium carbonate, the chemical reaction between the Fe2O3 and the K2CO3 forms a compound of 2 moles of KFO2 and carbon dioxide gas. That is 1 mole of carbon dioxide gas. As this is a solution, the potassium iron oxide further reduces to form iron 2 oxide. 1 electron was contributed as the iron 3 was reduced to iron 2. Therefore, the equivalence for this reaction is 1. The equivalent weight of the iron is therefore 55.8 grams equivalent weight per mole. The reduction of manganese 7 to manganese 2 has a reduction of 5 electrons. Now, using the GEW equation, the equivalent weight for manganese is 10.98 grams equivalent weight per mole. The term normalization is the method of converting molarity to normality. The term normal is in reference to the concentration of a species in a solution. The capital N is the designation for normality. The definition of normal, that is, N, is a solution containing equivalent weight, or GEW, of a substance contained in 1 liter of water. Now, the term is the expression for the number of equivalents contained in 1 liter, or milliequivalents dissolved in 1 milliliter of water. As with other references pertaining to concentration of a species in a solution, such as volume to volume or weight to weight, and so on, there is a relationship in regards to molarity. Grams equivalent weight is equal to the mass molecular weight of a substance divided by the number of equivalences. Molarity is equal to the number of moles of a substance divided by a liter of water. Normality, being n, is equal to the number of equivalences multiplied by the molarity of a substance in solution. It is also equal to the number of grams of a substance in a liter of water, divided by the gram equivalent weight of a substance. An example, the molarity of 0.01 molar hydrochloric acid in 1 liter of water is 0.01 moles. The molecular or mass weight of hydrochloric acid is 36.5 grams per mole. The equivalence of hydrochloric acid is 1 equivalent, or 1N. Therefore, the gram equivalent weight is 36.5 grams equivalent weight. Normality is equal to the molarity of a species multiplied by the number of equivalences. Now this equates to 0.01 normal hydrochloric acid. 0.0 molar hydrochloric acid is equal to 0.365 grams per liter, and N is equal to the number of grams per liter divided by the GEW, which is 0.365 grams divided by the 36.5 grams, which equates to 0.01 normal hydrochloric acid. Normality is used in reference to concentration for titrations. And in the next few slides, we will focus on more of the calculations used, starting with pH values that represents the strength of an acid or a base. These are used to determine the acid-base indicator to be used to identify the endpoint of titration. The final focus in this presentation will be on the determination of the concentration of species from the titration values obtained. At equilibrium, the acid is neutralized by the base. The neutralization is based on the solution's concentration of either the base or the acid. pH can be determined by using litmus paper or by using a pH meter. This can also be determined algebraically, but for now, it is important to know the equations that can be used to determine the strength of an acid and a base without a titration, although it is not as accurate as a titration. These equations are important when we look at selecting an endpoint indicator. This colorful graph is the pH graph of litmus paper showing the color formation of a litmus test. The pH graph starts at 0, and some graphs start at 1 and end at 14. There are times that it is possible to have a strength greater than or less than what the graph shows. There is also one more important value to know and remember, and that is Kw. Kw is the equilibrium constant for water. Kw is equal to 1 times 10 to the minus 14. Now Ka multiplied by Kb equals Kw. And Kw is the neutral point, or the neutralization point between an acid and a base. More on this later. Using a 0.01 normal solution of HCl, for example, the pH value is equal to the minus log of the molar value. As the equation shows, 0.01 is equal to 10 to the minus 2. The minus log of 10 to the minus 2 is 2. Using some litmus paper or a pH meter, the pH meter would read pH of 2. Knowing this value, the molarity of the solution can be determined. It is the anti-log of the pH value, or simply 10 to the minus 2 as shown. For a base solution, the process is similar, but there is one more step. The pH of 0.001 normal ammonium hydroxide, for example, equates to having a pH value of 3. However, ammonium hydroxide is a base substance, not an acid. The pH must be converted to pOH. Since the strongest base has a value of 14, the pH must be subtracted from 14 to show a pH value of 11, or a pOH value of 11, indicating the ammonium hydroxide is a base. Now, knowing the base value of ammonium hydroxide in a solution, The molar concentration can be determined, however. It must be converted back from pOH to a pH value. Since the pOH value was 11, the 14 minus 11 brings it back to the pH value of 3. The antilog, therefore, is 10 to the minus 3, which equates to 0.001 normal. In the previous slide, I mentioned that the pH value can be determined algebraically. Using an example, let's say a 0.05 molar ammonium hydroxide solution, the Kb table for ammonium hydroxide is 1.8 times 10 to the minus fifth. The equation shows that there is a small amount of ammonium hydroxide that does not dissociate at equilibrium. This was explained in a previous presentation in the series. Therefore, this minute or negligible amount can be ignored. Using some basic algebra, the unknown x is thus x squared. Now x squared is then equal to 1.8 times 10 to the minus fifth multiplied by 5.0 times 10 to the minus second, which is 0.05 mathematically, but in a notation form. Square rooting both sides of the equation as shown results in 1x, which equals 9.49 times 10 to the minus 4 molar. The pH value is equal to the minus log of 9.49 times 10 to the minus 4, or 3.02. Now, knowing that the ammonium hydroxide is a base, it must be converted. 14 minus 3.02 equals a pH value of 10.98 on the pH scale. If extreme precision and accuracy was required for this determination, then a quadratic equation would need to be used. However, since the remaining ammonium hydroxide is so negligible for a mineral assay determination, it can be ignored. This method of pH determination is useful when an ammonium solution or other solution is created, and a pH meter or some litmus paper is not readily available to be used. There are many examples of titration procedures, both in textbooks and online. Many will show that a titrating reagent is listed in normality instead of concentrations of volume to volume or weight to weight, etc. Remember that the GEW, or grams equivalent weight, is equal to the mass weight of the species divided by the number of equivalents. Now, as shown in an earlier presentation, the weight of a species weighed on a scale dissolved in 1 liter of water divided by the grams equivalent weight equates to the normality of the solution. Now, this slide shows that the normality of 8.29 grams of potassium carbonate dissolved in 1 liter of water has a concentration of 0.1200 normal, or 0.12 N. The pictogram shows that the mass weight of a species can be reverse determined for a given normality that may be required for a solution. Sulfuric acid is labeled as 98%. However, in small print, it will state 98.08 grams per mole. Now, this signifies that the 98% is weight to weight or weight to volume. The weight of water is 1 gram per milliliter or 1,000 grams per liter. Therefore, it could be weight to weight. A specific gravity table will show that the specific gravity for sulfuric acid is 1.080. Now, this may also be printed on the bottle's label. Using 50 mils of sulfuric acid that has been diluted to 11.60%, there are 4 steps that are involved to convert the concentration to normality. First is to calculate the gram equivalent weight of the sulfuric acid. The weight of the acid is 98.1 grams, mass weight. Since there are 2 hydrogen atoms for the formula, the number of equivalences is 2. So this equates to a gram equivalent weight of 45.05 grams. Next, the grams of sulfuric acid contained in the 50 ml solution will need to be calculated. Since the specific gravity of sulfuric acid is 1.080, it can be multiplied by the 11.6%, which is then multiplied by the 50 mils of solution. The grams of sulfuric acid equals to 6.264 grams. The third step is to calculate the molar concentration in grams per liter. This is achieved by dividing the 6.264 grams by the 50 mils, then multiplying by the 1000 milliliters, which gives a molar concentration of 125.28 grams per liter. The normality of the solution can now be determined by dividing the mass weight of 125.28 grams per liter by the gram equivalent weight of 45.05 grams. It can now be said that the 50 ml sulfuric acid has a concentration of 2.781 normal H2SO4. To take it a step further, consider a neutralization of sulfuric acid using the data from the previous two slides. Using the 0.1200 normal potassium carbonate to neutralize the 2.78 normal sulfuric acid, the amount of base needed for the neutralization can be determined. This formula shown was discussed in a previous presentation in this series. N1 is equal to N2, therefore, the equation N1V1 equals N2V2 can be used. The amount of potassium carbonate solution can be determined by multiplying the 2.78 normal sulfuric acid by the amount of 2.0 milliliters of the solution, then dividing by the 0.1200 normal potassium carbonate. The formula shown indicates that it will require 46.33 milliliters of potassium carbonate to neutralize the sulfuric acid. However, if the concentration of the sulfuric acid was not known, a titration could be conducted. If it took 46.33 milliliters to reach the end point of the titration, the formula N1V1 equals N2V2 can now also be used. The concentration can now be calculated by multiplying the 0.1200 normal potassium carbonate by the 46.33 milliliters of solution dispensed, then dividing by the 2.0 milliliters of sulfuric acid, as shown is 2.78 normal. Now, as shown, this method can also be used to standardize the sulfuric acid by titrating with a primary standard of potassium carbonate. A solution can be standardized by a method that is somewhat reversed. For example, adding a volume of primary standard solution of oxalic acid to an Erlenmeyer flask, along with an indicator, and adding a solution of potassium hydroxide of unknown concentration to a burette, the concentration of the potassium hydroxide can be determined. A primary standard solution containing 0.200 grams of oxalic acid is placed into the flask. A 50 ml burette is filled with the potassium hydroxide solution. 44.16 milliliters of the potassium hydroxide was dispensed to the end point. The potassium hydroxide has a mass weight of 56.1 grams per mole. The oxalic acid has a mass weight of 126.0 grams per mole. NKOH multiplied by VKOH is equal to the weight of the oxalic acid, divided by the equivalent weight of the oxalic acid multiplied by 1000 milliequivalents per equivalent. This now becomes NKOH multiplied by the 44.16 milliliters of dispensed KOH, which now equals 0.200 grams of oxalic acid multiplied by 1000 milliequivalents per equivalent, divided by 63.0 equivalent grams of oxalic acid. The equation now becomes NKOH multiplied by 44.16 milliliters, which now equals 3.1746 grams milliequivalents per milliliter. Therefore, NKOH is equal to 3.1746 grams milliequivalents per milliliter divided by the 44.16 milliliters equals 0.0791 normal potassium hydroxide. Many small-scale miners, prospectors, and hobbyists use cleaning vinegar to clean samples. Many labs use it for analytical purposes. Vinegar has, as the main ingredient in solution, acetic acid, which is CH3COOH. The strongest vinegar that I have found so far is 80%. Diluted, normalized acetic acid in solution will change in concentration at standing for quite some time. To be used, it must be analyzed, that is, titrated to determine its true concentration. In this example, phenolphthalein is used to determine the endpoint. 3.50 grams of sample is placed into a small beaker. The mass weight of the acetic acid is 60.00 grams per mole. The titrant to neutralize the vinegar at equilibrium is 0.1150 normal standard potassium hydroxide. 22.25 milliliters was dispensed at the endpoint. The grams equivalent weight of the acetic acid is 60.00 grams, as there is only one hydrogen atom that can be donated during the chemical reaction. The designation HA is just a designation for any acid containing hydrogen. It is equal in milliequivalents to the potassium hydroxide. Since there is 1,000 milliequivalents in 1 gram, 1.0 equivalent multiplied by the 1,000 milliequivalents equals N1V1. Therefore, the 0.1150 normal potassium hydroxide multiplied by the 22.25 milliliters dispensed multiplied by the 60.00 grams equivalent weight of the acetic acid divided by the 1,000 milliequivalents per equivalent equals 0.1535 grams of acetic acid. Since the sample weight is 3.5 grams, the weight of the acetic acid divided by the sample weight multiplied by 100 gives us a percent acetic acid of 4.386%. This example goes a little beyond normal mineral assay. However, in a laboratory setting, materials containing nitrogen as well as other non-metallic elements, those elements may need to be determined. This example demonstrates the complexity of a determination. An unknown sample that may contain nitrogen will need to be solubilized. A catalyst mixed with a sulfuric acid can speed up the dissolving process. Normally, about 1 gram of sample would be decomposed. Once the sample is fully dissolved, the acid would have to be neutralized. This can be accomplished by using sodium hydroxide as the base. To extract or liberate the nitrogen from the solution, it is then distilled. The output of the distillation equipment is captured in a beaker of hydrochloric acid. This excess of 0.2320 normal, 25.00 milliliters of hydrochloric acid is then titrated with a 0.2340 normal sodium hydroxide solution. 2.75 milliliters of sodium hydroxide was dispensed to the endpoint. Since the interest is in the nitrogen concentration, the distilled sample is what is used to determine the nitrogen concentration. The beaker contains 25.00 milliliters of 0.2520 hydrochloric acid. The milliequivalence is therefore 6.300. The amount of sodium hydroxide used for the titration to the endpoint was 2.75 milliliters. Its milliequivalent, as shown, is 0.644. The amount of ammonia collected would equal the 6.300 minus the 0.644, which equates to 5.656 milliequivalents for the ammonia distilled and captured. The milliequivalent of ammonia is equal to the hydrochloric acid, which is equal to the milliequivalence of the nitrogen. Since the ammonia is equal to 5.565 milliequivalents, then the weight of the nitrogen is 5.656 multiplied by the atomic weight of the nitrogen, which is 14 grams per mole. This value is then divided by the 1,000 grams equivalent weight. The grams of nitrogen then equates to 0.0779 grams. The percentage of the nitrogen present in the 1.0 gram sample is therefore 7.79% as shown. In this presentation, what a titration is, what its requirements are, the calculation used in regards to acid-base titrations. Yes, there is a lot of information in this presentation, and I sincerely hope that I was able to present this information in a way that would be understandable to any small-scale miner, prospector, and/or hobbyist that does not have a chemistry background, and that may be interested in conducting their own chemical analysis. In this presentation, the focus was on acid-base titrations, which are normally conducted for standardizing titrating reagents. I mentioned the use of indicators to determine the endpoint of a titration. Well, in Part 18, when published, it'll focus on the different indicators available and how to choose an indicator for a titration. If you found some benefit from this presentation, or know of somebody that may benefit from this presentation or series of presentations, please give it a like and a share. It's my only reward. I am Rob Boyko, Boyko Mineral Exploration, and I thank you for watching.